So, in the last lecture we looked at the various groups that are formed when you have multiple C n axes where n is greater than 2. Okay. And this pretty much will allow us to classify all the molecules into various groups. Okay. So, based on which operations are present, we can classify molecules into various groups. Now, if you look at the character table of any molecule, what you see in this are not the individual symmetry operations, okay, not the individual operations in the group, but what you see are the classes of operations. And so, what we are going to do is in this in the next few minutes is to look at the classes of operations and use the standard notation which is now common in writing various groups. Okay. So, finally, we will go to something called the character table, and in the character table what appears are not individual operations, okay, but actually classes of operations. Okay. So, we will just spend a few minutes discussing how to get these classes of operations, and then we will look at the notation that is used for character tables. Okay. So, we have already discussed this, we have already discussed in some detail the various classes of symmetry operations. We said that two symmetry operations are in the same class if they are related to each other through a similarity transformation. Okay. Another way of stating this is we will see this right now, and we will look at it through an example. Okay. So, let us take the group C4V. Okay. So, C4V is a group, and the various operations of this group you can work this out. These are E, the identity, there is a C4 axis, and C4 generates 3 more operations, C4, C4(2) and C4(3). I deliberately wrote it in this order. Okay. C4(2) is identical to C2. C4(2) is rotation by 180 degrees, which is same as C2. Okay. And then there are 4 sigma v planes. Okay. 2 of them are referred to as vertical planes, and 2 of them are referred to as dihedral planes. Okay. So, if you think of a you can think of a planar molecule. Okay. If you think of a molecule that is planar, then the C4 axis would be one that passes through this, and you would have these two as a sigma v axis, and these two being so this is sigma v, and these two are sigma d's. Okay. So, we have these sigma v's and sigma d's. Okay. C4V is not actually for planar molecules, but to illustrate the difference between sigma v and sigma d, I am using this geometry. Okay. Now, what you will show if you work out the group multiplication table, you can show that C4 and C4(3) are in the same class. Sigma V1 and sigma 2 or sigma D1 and sigma 2 are also in the same class. Okay. C2 is in a separate class, E is always in a class of its own. Okay. So, these are the various classes. Now, we will just look at we will take the example of C4 and C4(3), and we will show something that is in a sense we will explore further the relation of them being in the same class. Okay. So, we had stated this way of writing classes as defining classes as two operations in a group belong to the same class if one can be replaced by the other in a new coordinate system. Okay. So, essentially what we mean is that in one coordinate system you will have C4 one operation look like C4 and the other look like C4 cube. If you look in another coordinate system, first operation will look like C4(3) and the second operation will look like C4. Okay. But that is not all, this is not all. So, in a new coordinate system, and this new coordinate system should be accessible from the original one, through a symmetry operation in the group. Okay, so this part is very important. So it is very important that the two elements will be in the same class only if they can be replaced by the other in a new coordinate system. So in one coordinate system, C4 looks like one transformation and C4 looks like something else, and that something else looks like C4 in the other coordinate system. But then these two coordinate systems should be accessible from through a symmetry transformation, okay, through a transformation that is actually a symmetry operation in the group. Okay, and we'll look at this example. We'll look at this example. So let's look at so C4 is same as rotation by 90 degrees. Okay, so C4 you can think of as rotation by 90 degree about the z axis. Okay, so if you think of it that way, then if you have a coordinate system, I will call this coordinate system 1, where you have x and you have y axis. Okay. Now, if I take a point with coordinates x and y, okay, and I operate it by C4. So, C4 is rotation by 90 degrees, okay, and if you rotate by 90 degrees, then this point will come to this point. Okay. Now the x coordinate of this point is same as y, but the x coordinate has changed sign. Okay, so this distance is y, this distance is x. Okay. So when you operate C4 about z axis on an arbitrary point x y, okay, you get a point. So the new x coordinate is minus y and the new y coordinate is x. Okay. So this new point has coordinates minus y and x. Now if I rotate by 270 degrees, so C4 cube equal to rotation by 270 degrees or rotation by minus 90 degrees. Okay, so you can either rotate by 270 degrees or you can rotate by minus 90 degrees. So if I do C4 cube on z, so then it takes a point x y. Okay, now we can show what will happen. So if I rotate by minus 90 degrees, I will end up here. Okay, I will end up exactly here. So the point will be exactly y minus x. Okay. So it will be exactly opposite of this, that is y minus x. Okay. Now suppose I do the same thing in a slightly different coordinate system, where let us say this was my y and this was my x. Okay, if I had y and x defined this way. Okay. So if I had y and x defined this way, then you can see that C4 will take this point here. You can show that if you had a point with x coordinate as x and y coordinate as, this is the y coordinate, that is y, and let me call this coordinate system 2. So in coordinate system 2, I will call it C4 prime, just to distinguish it from that. So in this coordinate system, the point x y gets mapped to y minus x. Okay. So you can see that the x coordinate of this new point is same as y. So this is y, and the y coordinate of this new point, which is this distance, that is minus x. Okay. Similarly, C4 cube prime of z of x y, this is equal to minus y x. Okay. So, here we see the same C4 operation in this coordinate system, it takes x y to minus y x, whereas in this coordinate x y to y minus x. Okay. Similarly, C4 cube in this coordinate system takes x y to y minus x, and in this coordinate system it takes it to minus y x. Okay. So, you can see that C4 and C3 are interchanged. The effect of these two operations is interchanged in this new coordinate system. Okay. So, in other words, C4 prime is equal to C4 cube, and C4 3 prime is equal to C4. Okay. So, in this primed coordinate system, C4 and C4 cube have the opposite effect on the same point. Okay. Thus, we found a new coordinate system. Okay. We found a new coordinate system in which these two operations can be switched. Okay. Now, that is not all. You need these two coordinate systems to be related through a similarity transformation, okay, through a symmetry operation. Okay. So, what is the symmetry operation that takes this coordinate system onto this? Okay. So, in other words, what is the symmetry operation that takes y from here to here and take x from here to here? Okay. And you can see it very easily. So, if you had this as your y and this as your x, okay, now you want a symmetry operation that that leads to x here and y here. Okay. And it is very easy to see that the operation that you have has to be a reflection about this. So, if you reflect about this axis, then this becomes your x axis. So, if you imagine there is a mirror here, okay, that reflects it. So, x will come here, y will come here, and you will have something like this. Okay. Now, this reflection corresponds to a sigma d operation, okay, either sigma d1 or sigma d2, depending on how exactly you define the various axes. Okay. So, sigma d takes this coordinate system 1 to coordinate system 2, okay, and in these two coordinate systems, these two operations are interchanged. Okay. So, this implies, so since sigma d is contained in C4, okay, sigma d is one of these sigma d's is contained in C4V. Okay. So, you have an operation sigma d which is contained in the group, which transforms this coordinate system 1 to coordinate system 2 such that the C4 and C4 get interchanged in these two coordinate systems, and that is why you say C4 and C4 are in the same class. Okay. So, this implies C4 are in same class for group C4V. Okay. So, they are in the same class only if you have C4V group, only if you have this additional sigma d operation in the group that takes one to another. Okay. So, for example, if you had the group of pure rotations, a group of pure rotations like C4 would be a group of pure rotations where these operations would not be there. Okay. So, if you had a group of pure rotations, okay, then C4 and C4 are not in the same class. Okay. C4 and C4 turn out to be not in the same class for this group of pure rotations. In fact, if you have a group of pure rotations, then each of these elements is in a class of its own. Okay. So, now this way of understanding classes of symmetry operations is extremely useful, because this seems to suggest to you that there is something very similar about C4 and C4 3. Okay. There is something that is, they look like the same operation. Okay. So, these two operations are basically the same operation. It is just like you look at it in a different coordinate system, then this will look like this and this will look like this. So, these two are essentially the same operation. One is just rotation by 90 degrees one way, other is rotation by 90 degrees the other way. But if you had a coordinate system where one way looked like the other, then these two operations would get interchanged. Okay. So, there is something something that is very characteristics of these symmetry operations, and it is that operations that are in the same class. Okay. So, two operations in the same class, okay, they are related to each other through the simple coordinate transformation. Okay. And in a sense what we said is that the classes, okay, two operations, if two operations are in one class, okay, then those two operations are essentially equivalent operations. Okay, so two operations in a class are basically equivalent operations, and so this C4 and C3, okay, these two turn out to be in one class. Similarly, you can show that sigma V1 and sigma V2 turn out to be in the same class. Similarly, sigma D1 and sigma D2 will turn out to be in the same class. Sigma 2 is in a class of its own, E is in a class of its own. Okay. So since two operations belonging to the same class are essentially equivalent operations, it makes sense to group them together. Okay. And that is what is done typically when we write the character table of groups. Okay. So I will just do it right here. When we write the character table of the group, we divide the elements of the group into classes. Okay. So when we list the various operations of this group, so we will write it in this form E. Okay. Now there are two elements, two operations in the same class as C4. So we write it as 2 C4. Okay, then there is C4 2, which is same as C2. So we just write C2. This is 2 sigma V and 2 sigma D. So we write them in classes. Okay, so these are various classes. Okay, so these are the various classes in C4V. Okay, so these are the various classes of C4V, and this is one way to list all the operations. Okay, so the way to read this is that here is the identity operation. Then there are two equivalent C4 operations. There is one C2 operation. There are two equivalent sigma V's and two equivalent sigma D's. Okay. Now this notation in terms of classes is what is used in most of the character tables. Okay. So let's just try to write down the rules for writing such notations. So this is a new notation. Okay, and let's write the rules for this. So the rules are for each operation you can write the rules. So for inversion, represent by I. Okay, so the class is represented by I. So new notation, this is for classes. Okay, so if you have a center of inversion, you can have only one center of inversion in a molecule, and if you have that, then you just represent it by I. I is in a class of its own, so you just call that class I. Second is reflections. So if you had a sigma h, okay, sigma h is always in a class of its own, so you just call it sigma h. Okay, so sigma h will be in a class of its own. Now if you have a sigma v, if you have sigma v's, then you separate them into classes. Okay, so sigma v's and sigma d's are separated into classes, and you can have n sigma v in one, sigma v's in one class. You can also have cases where sigma v's divide themselves into various classes. So some sigma v's are in one class, you could have another sigma v prime in another class, and so on and so on, and then you could have sigma d's. Okay, and this which class you call sigma v and which class you call sigma v prime is quite arbitrary. Okay, so a good example is here. Here you had 2 sigma v and you had 2 sigma d. Okay, now you could have had more sigma v planes, okay, which happen to be in the same class, but not the same class as these two. Okay, then you would list them as n sigma v prime. Okay. The third is rotations. Okay. And here we have to consider two cases. If you had pure rotations, suppose you had Cn, Cn2, Cn3, Cn n minus 1. So, these are the various operations. Now, if each of these was in a class of its own, then you would list the classes in this way. Okay. So, if they were in the class of their own, you would list it this way. Sometimes what happens is, as we saw in this case, because of the additional symmetries, some of the rotations fall in the same class. Okay. So, for example, you could have had suppose you had C7, you could have a case when C7 has C71 or C7, C76, C72, C75, C73, C74. So, you could have this example where in C7, if you had 7 sigma v planes, then these two would be in the same class. Sigmas C7 is rotation by 2 pi by 7, C76 is rotation by minus 2 pi by 7. Okay. And if you had a sigma d just like in that case, then these two would be operations in the same class. Okay. So, then this class you call it as 2 C7, this class we will call it as 2 C72, this class you will call it as 2 C73. Okay, and so on, and you can do this for other operations. Okay. So, when these two are in the same class, okay, so if these are classes, okay, now these two will be in the same class only if there is a sigma operation that helps you transform coordinates, so that one looks like the other. Okay. Now, if for example, if you had C6 you could have had C6, C65, these two could be in the same class, C62 which is equivalent to C3 and C64 which is equivalent to C32. Okay. Then you could have had C63 which is equivalent to C2. Okay. So, these two with the class is called 2 C6, this it is called 2 C3 and this it is called C2. Okay. So, you have two classes containing two elements and one class containing one element. Okay. So, this is the way you list the various operations, you break them into classes and then you use this notation for the classes. Okay. And just as we did for the proper rotations, you could do the same for improper rotations. So, improper rotations follow same notation. Follow same rules. Okay. So, instead of C's you have S. Okay. So, if you had an S6, okay, S6 and S65 would be in one class, S62 and S64 which is they would be in the same class and so on. Okay. So, now that we have seen how to separate the various operations into classes, we can now go ahead and give the procedure for classifying various molecules into groups. Okay. So, this is a procedure. This is a procedure for identifying group. Okay. So, the idea is you have a molecule, you have all the symmetries. Suppose you know all the symmetries, how do you identify which group it lies in? Okay. And this is a summary of what we have been talking about in the last 2 or 3 lectures. So, this is a summary. Okay. Okay. So, how do you go about identifying the group in which a molecule should lie? Okay. So, the first thing, look for special groups. Okay, so the special groups, I mean linear molecules and molecules with multiple Cn axis where n greater than 2. Okay. So, first you check whether your molecule is linear. Okay. If your molecule is linear, then the group will be C infinity or D infinity. Okay. So, if your molecule is not linear, you will see whether your molecule has multiple Cn axis where n is greater than 2, and this is, so if it has, then it has to be one of the 7 groups T, Td, Th, O, OH, I, IH. So, it has to be one of these 7 groups. Okay. So, if it has multiple Cn axis where n is greater than 2, it has to be one of these 7 groups. Okay. So, first you check whether it falls in one of these special groups. If not, then you look for molecules that have no proper or improper axis of rotation. So, if a molecule does not have any proper or improper axis of rotation, then it will be either a totally asymmetric molecule, that is C1, okay, or it can be a molecule with a center of inversion, okay, or it can be a CS, okay, with that just has mirror planes. Okay. Then the third. So, first you look for special groups that are linear molecules or molecules with multiple Cn axis. Then you look for molecules that do not have any proper or improper axis of rotation. Okay. Then you look for molecules that only have Sn. Okay, and obviously n has to be n even. So, only Sn where n is even. Okay. So, if Sn is even, okay, so Sn2 is same as Cn by 2. Okay. So, it has only Sn axis where n is even. Okay. Remember Sn contains Cn by 2. Okay. So, if it only contains Sn, then the name nomenclatures like S2, S4, S6, etc. Okay, so it has to be one of those groups. Then the fourth one is only one Cn axis for n greater than 2. So, when you have only one Cn axis for n greater than 2, then there are 2 cases you can have. You can have one case when there is, so the 2 cases, the first case is no perpendicular C2 axis. Okay. So, you do not have any C2 axis that is perpendicular to this Cn axis. Okay. Now, you should recall that if you had a C2 axis that was perpendicular, then you would have n other C2 axis. Okay. So, in this case, if you have no perpendicular C2 axis, okay, then you can have either you can have Cn where you have no sigmas, or you can have Cnv, or you can have Cnd. Okay. So, if you have a vertical plane of reflection or a dihedral plane of reflection, it will be either Cn or Cnv or Cnd, sorry, or Cnh. Okay. So, if you had a horizontal plane of symmetry, then it would be Cnh. Now, the other case is if we have perpendicular C2 axis, Okay. So n C2 axes that are perpendicular to the Cn axis. Okay. Then you can have three cases. So the corresponding cases will be dn and dnd or dnh. Okay. So in this case it will be a group of, the name of the group will be either dn, dnd or dnh. Okay. So this little chart will help you look at the various operations, various symmetry operations of a molecule, and identify and assign it the appropriate group. Okay. So this whole procedure is a summary of what we have been discussing so far. Once you have all the operations, then you can go ahead and you can tell which group the molecule lies in. So let us do an example of this. This is the Allene molecule. I will take an example. Allene. Okay. So Allene molecule has C, and now this has 2 hydrogens and this has 2 hydrogens. Okay. Now these 2 hydrogens would be, if these 2 are in the plane of the paper, then these 2 will be perpendicular to the plane of the paper. So there will be one going in and one coming out. Okay. So that is what the Allene molecule will look like. Okay. Okay. So let us list all the symmetry operations of this molecule. Okay. Now you can show that this axis is an axis of rotation, and this axis is an S4 axis. Okay. It is also a C2 axis. Okay. So this is an S4, it is also a C2 axis. Okay. In fact, S4 square, S4 itself generates C2, because if you operate S4 twice, you will get a C2 operation. Okay. But there is no notice that there is no sigma H. Okay. There is no sigma H in this molecule. Okay. There is no sigma H and there is no C4, but there is an S4. So also you can see that since these 2 hydrogens are equivalent, so if you can have a C2 axis here and a C2 axis here. So these 2 are also C2 axis. Okay. So these 2 C2 axes will turn out to be in the same class. So we'll call them 2 C2 prime. Okay. Then this has a C2 which is generated by this S4, that will be in its class of its own, and then there will be S4 and S4 cube. So that is 2 S4. Okay. So these are the various operations. Okay. And then there should be a dihedral plane. So there should be two dihedral planes. One is perpendicular to the board and one is in the plane of the board. Okay. So there will be 2 sigma d's, and these 2 are equivalent. Okay. Okay. So you can list the various classes in this way, and so there are 2, 4, 6, 7, 8 operations. Okay. And this, if you follow this classification scheme, you have one Cn axis, that is one S4 axis. Okay. You have one S4 axis, and you have no perpendicular C2 axis. Okay. So this you can show that this is in D2D. Okay. So it is D2 because this is a C2 axis. Okay. And it's C2, and there is no perpendicular C2 axis. Okay. So these set of operations give it, this group is called D2D. The size of this group is order of D2D equal to 8. Okay. Okay. So, next what we want to look at is the representations of these groups. Okay. Okay. So, let us look at some examples of how we would identify the symmetry group of various molecules based on their structure. Okay. Now, the examples I will take will be illustrative of all the rules that we have discussed so far. So, we looked at the allene molecule. Now, we look at some other examples, and you should actually go back and try to verify some of the things that we are saying here. Okay. So, let us take the case of 1357 tetramethyl cyclooctatetraene. So, this is basically a molecule that looks like this. Okay. So, it has 2, 3, 4, 5, 6, 7, 8. So, it is a cycloocta, and there are 4 double bonds tetraene. So, and it is 1, 3, 5, 7. So, this is the tetraene, and there are 4 methyl groups. Okay. So, this is cyclooctatetraene, okay, and there are 4 methyl groups located at 1, 3, 5 and 7. So, you can put one methyl group here at alternate 7. Okay. So, there are 4 methyl groups. This is the molecular structure of this molecule. Now, the 3-dimensional shape of this molecule turns out to be a little complicated, but you can work it out. So, basically what happens is you imagine that that 4 of these 3 and, or you can imagine this way, that 3 of these form a sort of a structure like this. Okay. There are 3 more that form a similar structure on that side. Okay. These these 4 carbon atoms, 1, 2, 3, 4 and 3 bonds, they form a structure like this. There is another parallel structure like this. Okay. It is, you should actually imagine it being directly behind this, and these 2 are joined at this through a bond between these 2. Okay. So, this is a structure, and you can see that there are the symmetries of such a molecule will be in general a little hard to determine. Okay. And you have to really know which direction the methyl groups point and so on. Okay. Now, this is a double bond. So, each of these are double bonds. Okay. So, if you know that these are double bonds, then you can immediately you can identify a few things. We'll write this out here. So, you have a methyl group. So, the methyl group comes this way, okay, and you have this coming this way. Okay, you have a hydrogen here. Now, directly behind this, in the plane of the board, you have another such groups. So, I'll show it in front. So, it will be something like this. Okay. So, you have something like this, and in this case, now the methyl group will be here. So, just imagine these 2 structures, and now imagine that you connect these 2. So, if I connect these 2 with a double bond, these 2 with a double bond, this is basically my cyclooctatetraene. Okay. And then if I put methyl groups here and another methyl group here. Okay. Now, what you notice is that because of these methyl groups, okay, a lot of the rotation symmetries will be destroyed. Okay. What you also notice is that if you imagine an axis that passes right in between this, so something like this. Okay. So, just this axis, okay, this axis is an S4 axis. Okay. It is S4 because if you rotate it once, then I mean you can see it from here. If you rotate once, then basically this double bond will come here, and then you reflect it about a perpendicular plane. So, then this double bond will go to the, it will come here, and that will be completely symmetric with the original figure. Okay. So, this has an S4 symmetry about it, okay, because you can you can see that it's a you can see that by looking at this structure. So, you imagine that you rotate it once, okay, then if you rotate it, then if you rotate it by 90 degrees, then this will face sideways. Okay. So, then what has happened is that your double bonds are they appear in the opposite places. So, when you reflect it, then you will find that the double bonds appear in the right place and the methyls are pointing in the right directions. So, this is an S4 axis. Now, because of these methyl groups, okay, all the reflection symmetries are destroyed, okay, because when you reflect about various planes, then the methyl groups will start pointing in different directions, and so those reflection symmetries are destroyed because of this methyl groups. Also, the methyl groups will also destroy any C2 axis that could have been present. Okay. So, this has S4 and nothing else. Okay. So, it has only an S4 and nothing else. So, this is the point group for this molecule is S4. Okay. This is the rule you remember, if a molecule has S4 group and nothing else, okay, if it has S4 group and nothing else, then the point group of the molecule is S4. Okay. So, it has an S4 operation and nothing else. Okay. Only in that case it falls in point group S4. If it has S4 plus other operations, then it will not be in S4 anymore. Okay. So, an example of that is, suppose you just take cyclooctatetraene, okay, which is the same molecule without these methyl groups, the same as this molecule without the methyl groups. Okay. Now what happens is, when you do not have these methyl groups, you have additional symmetries, and you can see some of them. You can see that you have two perpendicular C2 axes. Okay. You have two perpendicular C2 axes. In addition, this S4 axis is also a C2 axis. Okay, S4 axis also becomes a C2 axis. Okay, because you rotate by 180 degrees, this double bond will go exactly here. Okay. When you had the methyl groups, you rotate by 180 degrees. The problem was that these methyl groups would not point in the right directions. Okay. So, that was the reason it was not for example, if you do a C2 operation on this, okay, then you can see that that this will cause these methyl groups to point in different directions. Okay. So, if you do not have methyl groups, then this has this S2, this S4 axis is also a C2 axis. In addition, you have these two perpendicular C2 axis, we call them C2 primes, okay, and these are perpendicular to this S4 axis. And then you also have sigma v's, these bisect the double bond. So, if you imagine a plane that passes through this through the center of both these double bonds, okay, that would be a reflection plane. Okay. So, if you reflect about this, then this atom would come here, 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 and then similarly the other atoms would get reflection on this side. Again, that was a symmetry that was absent in the molecule with the methyl groups. Okay. So, the presence of the methyl groups again destroyed that reflection symmetry that you had. Okay. So, now since this has more than an S4 operation, okay, it also has other operations. Okay. So, therefore, it is not in a, you cannot say that the point group is S4. Okay. So, now the point group is determined by the Cn axis. Now it is C2, okay, and you have sigma v. So, C2 plus sigma v, that determines that implies that it should be D2D. Okay. So, the point group of cyclooctatetraene is D2D, okay, whereas that of tetramethyl cyclooctatetraene is S4. Okay. So, this is an example of illustration of the rules. Okay. I'll show you one more well known example. Okay, but again it is important that you go back and verify each of these rules. Okay. So now let's look at the staggered configuration of ferrocene. Okay, now ferrocene, if you remember, the structure was something like this. So this was your ferrocene structure. Okay, and the staggered configuration, these two pentagons are not exactly aligned. So the way you would show it is that you would show one pentagon in one direction and the other pentagon in the opposite direction. So you would show something like this. Okay, so these, you have this Fe. Okay, so now and these two pentagons are essentially planes. They are perpendicular to the plane of the board. Okay, so you have a pentagonal structure there and another pentagon that is staggered from this original pentagon. Okay, so now what are the various symmetry operations? Now since they are staggered, okay, this first thing you notice is that if there is a, let's see, there should be a S10 operation. Okay, so there is an improper axis S10, okay, where you rotate. You can imagine it this way. So this axis, okay, so this axis is an S10 axis. Okay, so if you rotate it by 2 pi by 10, then this triangle will come right here. Okay, this bond will end up here. Okay, and when you reflect it, it will get reflected onto this. Okay, so it's an S10 axis. Okay, so this axis is an S10 axis. Okay, but there are other axes. Okay, there are other axes also. First thing is that this is a C5 axis. Okay, this is also a C5 axis. So S5, S10 plus others. Okay, now this is a C5 axis. Okay, and what else can you say? What else is there? So you can see that there will be 5. So there's a C5 axis, phi C2 axis. Okay, so there are 5 C2 axes that sort of, I mean, you should think of in this direction. Okay, so there are 5 of these C2 axes. Okay, so if you have one C2 axis, there have to be 4 other C2 axes, and then you can easily show that there are 5 C2 axes in this plane. So these are perpendicular to the plane of the board, and they will be in various directions. Okay, and there are 5 sigma v. Okay, now since it has, in addition to S10, it has a C5. Okay, so the nomenclature is dominated by C5. So this is C5 plus phi sigma v. So it is D5 T. Okay, so this is ferrocene staggered. Okay. Now what about the eclipsed conformation? What about ferrocene eclipsed? Okay. Now in the eclipse conformation, you have essentially something like this. Okay, so these two are in the same direction. Okay, so the two pentagons are both pointing in the same direction. So now this is C5 axis. So you have C5. Okay, now this plane is a plane of symmetry now. So this is a reflection plane. So there's a sigma h. Okay, and then so now the nomenclature of the group will be dominated by this by the C5, okay, and it has sigma h. It has the vertical planes, as before it has various vertical planes, sigma v, C2, etc. So, this is D5H. Okay, the presence of sigma h tells you that it is D5H. Sigma h, C5, 5 C2 and sigma h. So, this is D5H. Okay. So, what we have seen is that just the same molecule, it looks like just slightly different conformations, and you get and they belong to completely different symmetry groups. Okay. If you take something in between, then you will get a different group for that. Okay. So you will get something in between these two, and you cannot exactly say what this is. Okay. So if you take anything else in between, so in between staggered and eclipse, Okay, so if you take anything in between, so where these two are not exactly in the staggered or the eclipse conformation, then the group will be you will definitely have the C5 axis. So you will still have the C5 axis, but you won't have other groups. Okay, so it could be D5. Okay, so you have C5 and you have 5 C2, so that implies D5. Okay, so this example shows you how the molecule ferrocene in different conformation actually has different symmetry elements. Okay, and it belongs to different point groups. This part will become very important when we are actually looking at the spectroscopic signatures of the transitions of ferrocene.